Okay, so first let's look at this phenomenon of the problem with defining a velocity or a speed for a wave is that, okay, for monochromatic waves, we can talk about a well-defined speed for the wave, but when we don't have a monochromatic wave, so what is the meaning of speed? You see, for the monochromatic wave, okay, we can define a velocity for that or a speed for that, but a monochromatic wave is basically of infinite length and of infinite duration. No wave in this sense is monochromatic. So in reality, we never work with monochromatic waves. We might have good approximations to a monochromatic wave, but not exactly equal to monochromatic wave. And in real life, what we have is we usually have the sum of various waves. Now you see, here you have, if you just look at the second line at the top, this is the wave that is made up of the sum of two harmonic waves, two cosines. These two cosines differ by, they have almost the same k. The k value is 10. One has the k value 10, the other one has the k value 12, just 20% different. And if you look at the angular frequencies, one has the angular frequency 1, the other one has the angular frequency 2. So they just differ by angular frequency, they differ by their wavelength. Not much, I mean, they don't differ by an order of magnitude, but they both are at the same order of magnitude. And basically, this is how the wave looks like. Let me slow it down. So you see, here we have a zero of, the amplitude is very small over here, and it is moving. So, or look at this part. This part you can just treat it as a lump of energy. So the wave carries energy. So here we have a lump of energy which is moving slowly. At the same time, look at the peak value. You see the the peak value is moving, but you see the motion of this wave, just look at the maximum of this one. To follow the maximum, it goes to the zero of the wave, and then it's over here, then it just goes to the other wave packet. So the maximum of the wave and these packages, they move at different velocities. So that's basically the main reason why I'm showing you this graph. So on one hand, we have the motion of this maximum of the wave, which we call the wave velocity or the phase velocity. On the other hand, we have this package, the velocity of this package, which we call the group velocity. Well, if they were moving at the same speed, now if they were moving at the same speed, so this peak value should stay exactly the same. Now let's see what should be you see the wave velocity of one of them, this first cosine. The wave velocity is just omega over k, which is 1 over 10. The wave velocity of the other one is omega plus delta omega is 2 divided by 12. That is, well, 1 over 6. So these two waves, they have different velocities. Essentially, this is a system in which the wave velocity, the phase velocity depends on the frequency. We have one frequency of 1 hertz, let's say, which moves with a speed 1 over 10 meters per second. The other one oscillates at 2 hertz. It moves with a speed 1 over 6 meters per second. Now let's see what happens in a non-dispersive medium. How does this differ in a non-dispersive medium? Your friend says that, okay, they seem to be moving at the same speed. So let's say if the omega is 2 and the velocity was to be 1 over 10, the k vector should be 20, so delta k should be 10. K is already 10, we should add another 10 to it. So let's see how that behaves. how that differs from this wave. So you see, the shape almost doesn't change. The peak is always over here. On the other one, the peak was shifting relative to the package. So this is the tube. The main difference between a dispersive medium and a non-dispersive medium is that in a non-dispersive medium, the wave moves with the same shape. In a dispersive medium, the shape changes. You see, here the shape is changing. And so we define two velocities, one the phase velocity, one the group velocity. Well, of course, you can just change the number of definitions. In your book, there is a reference where they define 8 different kinds of velocities. So you see, the problem is you have velocity, the concept of velocity is well defined for a point object. That doesn't change its shape, that doesn't change its extent, etc. It stays as a point object. But here we have an extended object. How do you define the velocity of such an extended object whose shape is constantly changing? So there are various methods of obtaining this, defining the velocities. And from time to time you hear the news that, okay, they have violated Einstein's law. Einstein's law is now not valid anymore because they have created some waves moving faster than the speed of light. Okay, some of these waves, like we have 6, 7, 8, at least 8 of them, some of these speeds can be larger than the speed of light. You see, just imagine this. Just imagine you have a laser pointer and you are just shining it to the stars. If you move it fast enough, the tip of that laser pointer will move faster than the speed of light. No problem with that. But we are not sending any, we cannot affect anything at a speed faster than the speed of light. Even in these cases, even in the cases where you hear that, oh, they have violated the speed of light constraint, something happens faster than the speed of light. What is actually happening is not the transfer of information or not, you cannot cause anything at a speed faster than the speed of light. Okay, so after this small introduction, let's come back to our case where, as I had claimed, I would like to first see, is it possible to have the dielectric constant position dependent? Frequency dependent, sorry. Permittivity. Now, to obtain this position frequency-dependent permittivity, I will just assume a simple model. So here we have our material, our dielectric. Now, in this case, I will just ignore that. I will not take a conducting medium. I will just take well, you can just either treat it as a non-conducting medium where the electrons are bound to their atoms, or you can say that even for a conductor this will apply. There will be, in a conductor, if you consider a conductor, a metal for example, there will be some charges that are free to move around. Some electrons will be free to move around in a metal, but there will be some electrons that are fixed, that are attached to their nuclei. They cannot move around. And so they will be polarized. So that's why even a conductor, we have this polarization constants, etc. So the simplest model. This is the nucleus. This is your electron. They're attached by a spring. Now, this is not a very realistic model. Nevertheless, it serves our purpose of demonstrating some of the possibilities. Now, I will assume an electric field in the x direction, at the position, in the x direction, at the position of this electron. So at this, that's why I don't have any time dependence over here. Any position dependence, or because this is the electric field at the position of the electron. Now, what is the equation of motion of the electron? Well, this is mass times the acceleration in the x direction, let's say. Newton's law tells me that this should be equal to the force acting on it. The force acting on the electron is minus k times x, x being the displacement in the x-hat direction of the electron from equilibrium point. So since at the equilibrium there is no force, this is just a spring force. And there is this external force. Let's just put Q, which this is the charge of the electron, times E0 e to power I omega t. And we might have some dissipation. As the electrons are moving, it will lose some of its energy. The energy can go to other electrons, other nuclei, they can collide, etc. So let's just model this dissipation by a simple velocity-dependent damping term. Let me put the mass also over here. So this will be basically how the equation governing the motion of the electron.
Electron dönüyor.
Well, in the simple model, it's just also moving up and down in the x direction, in the direction of the electric field. Of course, you can create a more complicated model, a three-dimensional model where there will be a spring, the electron is free to move in all three dimensions, etc. It will just complicate the discussion without really adding new insights. So here we are building a very simple model that might help us to understand some of the phenomena that we observe. So if you need, for some reason, a more specific, concrete, detailed model, well, you can build one. But this very simple model will allow us to understand some of the phenomena. It will be enough for our purposes. md squared x by dt squared plus m gamma dx by dt plus k times x, this is equal to q times E0 e to power I omega t. Remember, this k is the spring constant. It's not the wave vector, it's the spring constant. Well, we need to solve this equation. Well, the easiest way to solve this differential equation is x is equal to some amplitude multiplying e to power I omega t. Yeah, of course, there will be some transient motion, but after all that motion dies away, the electron will basically oscillate with the frequency of the applied electric field. That's our driving force. And this coefficient A just turns out to be QE0 divided by minus m omega squared plus I m omega gamma plus k. This is our A, the amplitude. Now the dipole moment corresponding to this electron is nothing but q times x. We already know what x is, so this will be equal to q squared divided by minus m omega squared plus I m omega gamma plus k times E0 e to the power I omega t. Let's keep in mind the electron is moving in the x direction, the electric field is also in the x direction. So the polarization is q squared over minus m omega squared plus I m omega gamma plus k multiplying the electric field. You say E0 e to the power I omega t is nothing but the electric field. You see this is the polarization of a single electron. If you multiply this with the electron density, you get the polarization density. So the polarization density is just n times q squared, or let's say 1 over v. Polarization density is just, you just sum over all the polarizations in your medium, divide by the volume, in a given volume, divide by the volume. Qi squared, or let me use the symbol j, 1 over I m omega j mj gamma plus kj minus mj omega j squared E. Well, different electrons can have different frequencies. They can have, well, so here we are talking about electrons, they will all have the same mass. But in principle, you can have different charges, having different masses, having different damping coefficients, having different frequencies. Now, the omega j is omega. Omega is the frequency of the electric field, not of the charges. But you see, this is the polarization density, which we defined as chi e times E. This is the electric susceptibility. And the electric permittivity, this is epsilon 0 times chi E. Electric permittivity, remember we had defined this as epsilon 0, 1 plus chi E, which is epsilon 0 times 1 plus, well, for simplicity, let me just assume that all the gamma j's or all the mj's are the same. Some density q squared divided by omega k minus m omega squared plus I m omega gamma. Well, there are basically two things. One, it's imaginary, it's not real. Two, it depends on the frequency. Well, there are various cases you can consider. For example, you see this, let me define k over m as omega 0 squared. You see, this was our differential equation. If there is no dissipation, there is a characteristic frequency of this oscillator, and this oscillating frequency, it's just an oscillator with frequency squared k over m. So that's why I'm defining this k over m as omega 0 squared. So this epsilon is epsilon 0, 1 plus nq squared over m divided by omega 0 squared minus omega squared plus I omega gamma. Now, in general, gamma is small. The damping coefficient for a single electron will not be large. So if omega is far away from omega 0, this number is large, so we can just ignore this. So the electric permittivity is a real number. It is still frequency dependent, but nevertheless it's a real number. If you are close to one of these frequencies, omega is equal to omega 0, then this is small. You cannot ignore this. Since you cannot ignore that one, epsilon is now imaginary. It has an imaginary part. Now, where does epsilon enter our calculations? You see, we have e to power, the electric field, for example, is E0, e to power I kz minus omega t. Omega is a real number. And there is a relation between k and omega. This is a non-conductor. So k over omega is equal to 1 over v, which is 1 over square root of epsilon mu. Well, in general, mu will also have a frequency dependence. It can have an imaginary part, but the deviation of mu from mu0 will be negligible. But nevertheless, you see, epsilon will be what mainly determines this velocity. But if epsilon is complex, omega is a real number, that means k is a complex number. But if k is a complex number, we had already seen one case of k being complex, which was the conductors. If k is complex, then the real part, k tilde, let's say, again, since it's complex, I can talk about its real part, which is what I will call the wavelength, the wave vector, and it has an imaginary part. The imaginary part causes damping. So you see, we had already seen one case where the electromagnetic wave cannot move through a medium. That was the case when we have a conductor. Because in the conductors, the currents that it creates, it damps, it steals, let's say, the energy from electromagnetic wave. Here we have another cause of that damping, that gamma term. And so as the electrons are moving, they will collide with, although they are not free, they are not conductors, they are not conducting electrons. Nevertheless, as they are moving, they will just transfer some of its energy to the nuclei, to the other electrons, etc., and it will just take away the energy from the electromagnetic wave, which will cause the electromagnetic wave to damp as it moves through. That happens when kappa is non-zero. That happens when k tilde has an imaginary part, while k tilde has an imaginary part when epsilon has an imaginary part. The mu deviation from mu0 is negligible, so the imaginary part of mu will be negligible. So when epsilon has an imaginary part, we will have damping. The electromagnetic wave will not be able to penetrate.
1 over v is the square root of 1 over the square.
1 over v is the square root of epsilon mu. 1 over v squared is 1 over epsilon mu. So you see, when epsilon has okay, let me just repeat my argument. This k tilde, when it has an imaginary part, kappa over here, it tells me that as the wave is moving in the z direction, its amplitude will get smaller and smaller. It cannot propagate. It will just disappear in my medium when kappa is non-zero. One example we had already seen in the conducting case, where we had seen that, okay, we send the electromagnetic wave creates currents, and well, if it's not a perfect conductor, it will dissipate the energy of the electromagnetic wave, so the energy in the electromagnetic wave gets smaller and smaller. Now here we see another example of this case. The origin is similar but somewhat different. Similar in the sense that k is non-zero if epsilon has an imaginary part. Well, epsilon has an imaginary part if there is damping in the motion of the electrons. These are not necessarily conducting electrons. Nevertheless, although it's not a conductor, the electrons, due to this polarization of the medium, the electrons can shift slightly around their equilibrium position. So that motion around their equilibrium position is what causes this damping. Now, in general, that damping will be negligible if omega is different than omega 0. But if omega is close to that omega 0, that damping will not be negligible. The imaginary part will be large. And so the wave will not be able to propagate. So the question is basically, what are some possible values of this omega 0 in our medium? For most materials, these frequencies are kind of almost randomly distributed. So whatever wavelength you send, it will be close to at least one of those resonance frequencies. And since it's close to one of the resonance frequencies, the imaginary part of this electric permittivity will be large. If the imaginary part is large, we have this K. Well, the electric field is proportional to e to power minus this kappa z. The intensity is proportional to e to power minus twice kappa z. This twice kappa is called attenuation coefficient, if I'm not wrong. Or absorption coefficient. So it will be absorbed. Well, it's given a name alpha. If you are close to, of course it depends on the frequency. So if you are close to a resonance, that alpha will be large. So all the wave you send will be absorbed, so nothing will go through. If you are far away from those frequencies, for example, for glass, let's say, those resonance frequencies are in the ultraviolet. So if you send a frequency, if you send some light in the visible spectrum, then this omega minus omega 0 for the visible spectrum for glass is a large number. So this will be very small. The imaginary part of epsilon is very small. Since the imaginary part is very small, our wave will just propagate through the glass. But if you send some ultraviolet light, well, ultraviolet light its frequency is close to some of the resonance frequencies of glass. So this number will be small. The imaginary part of epsilon will be large, and hence this absorption coefficient will be large. And since the absorption coefficient is large, the ultraviolet light will not be able to penetrate glass of some thickness. Of course, it depends on the thickness. You see, if the thickness of the glass is very thin, or if you take any material, if you cut it thin enough, it becomes transparent. Because Z is very small, so the wave that you send is not absorbed significantly, so it just goes through. Wood, take the example of the wood. If you cut wood thin enough, you can just see light through. It doesn't become like glass. To have a wood that is just transparent as glass, you have to cut it really thin.
Şimdi hani elektron enerji kaybediyor dedik ya hocam. Biz dışarıdan elektrik alan mı gönderiyoruz yoksa nükleustan dolayı oluşan elektrik alanından mı enerji alıyoruz?
Well, we are sending an electric field. You see, look at our solution. We are sending a wave. I have my material. Okay, so just look at this book. I have the book. I sent some electromagnetic wave. And, well, some of it will penetrate some distance, depends on this absorption coefficient. It will penetrate some distance, and it will exert a force on the electrons, making my book. Now, if you just consider one electron, at that point, what that electron will feel is an oscillating electric field. So I just write that oscillating electric field in this form. This is the oscillating electric field that the electron at a given point feels. And starting from that expression, I found that the polarization of the electron due to the applied electric field is proportional to the electric field, but the proportionality constant depends on the frequency of the electric field. Well, that proportionality constant is what we call the dielectric constant or the electric susceptibility. If you remember our discussions in electrostatics in medium. But at that time, we just said that, okay, this dielectric constant or the electric permittivity is just a constant. Well, now we see that it's not really that constant in the sense that it has a different value for each frequency. For different frequencies, it will have a different value.
Benim kafama hocam şey takıldı, hani elektron enerji kaybediyor dedik ya, o zaman elektromanyetik dalga göndermezsek elektron nükleus'un üstüne düşmesi.
You see, this is a simple model. We have a very simple model where we are saying that the electron, if there is no external electric field, the electron is at rest over here.
Nükleus'un üstünde.
Yeah. This is a classical model. It's just at rest at this point. But when I send an electric field, I'm just causing it to vibrate. As I said, this is a very simple classical, it doesn't take into account the quantum mechanical effects, etc. It doesn't take into any other effect, actually. It's a very simple model. But it's a model that we can study explicitly, and we can drive some conclusions. Like, you see, this is in this very simple model, even this very simple model, the dielectric constant, or the electric permittivity, is a function of the frequency. That is what is crucial over here. Secondly, even observationally, we know that there are certain resonance frequencies. Even quantum mechanically, there are certain resonance frequencies where the electron can absorb energy. So if you are close to that resonance frequency, so here we see that if you are close to the resonance frequency, why there is, you see, if omega is very close to omega 0, in this very simple model, omega is very close to omega 0, so we are driving, let's say, our electron in its resonance frequency, so it will absorb a lot of energy from the electromagnetic wave, but it dissipates it. It doesn't give it back to the electromagnetic wave, it dissipates it due to this term, due to this damping coefficient. So what happens is, if you are close to the resonance frequency, this term is 0, so epsilon has a large imaginary part. Remember, gamma is a small number, that's what we claim to start with. The dissipation is small, but omega is very close to omega 0, so this term is almost 0, so this imaginary part is proportional to 1 over gamma, which is a huge number. So close to this resonance, gamma becomes very, kappa, which is related to the imaginary part of epsilon, becomes very large. If kappa becomes very large, the electric field only exists for very small values of it. So if you have this medium, you send some electromagnetic wave in this interface. After this interface, the electric field changes by e to the power minus kappa z. That is how the electric field from this surface into the medium changes. So let's say it just decays exponentially. So look at this graph over here. The amplitude decays exponentially. And since it decays exponentially, you see here at this distance, you cannot really say that there is a wave anymore. It's almost 0. So basically the same thing happens over here. You send your wave onto your medium. In your medium, you send your wave onto your medium. In your medium, the electric field decays. Well, once the electric field is 0 over here, and your medium ends over here, well, there's no electric field to go on the other side. There's none of the wave passes through. So if this distance where your electric field becomes almost zero is very narrow, very small, let's say 1 millimeter, and if you create some glass from this material which has a thickness 1 centimeter, well, none of this electromagnetic wave will pass through. What happens in these transparent objects like glass is you send your wave, and the frequency, the visible frequency, is not close to any of these resonance frequencies. And since it's not close to those resonance frequencies, the imaginary part of the permittivity is negligible. Since the imaginary part of permittivity is negligible, the imaginary part of epsilon is negligible, k tilde is a real number. There is no attenuation of the wave. The wave amplitude stays the same throughout the material. Of course, this is also valid if the thickness, still epsilon has a very small imaginary part. So if you create a very thick glass, like 1 meter, 2 meter thick glass, still not all of the wave will pass through, but most of it still goes through. So that's why thin glasses of thickness a couple of centimeters is transparent.
Bir şey daha sorabilir miyim? Şimdi biz burada hani damping törmetledik ya. O zaman nükleus elektron arasında bir madde mi var yani damping?
Well, you see, we are talking about a material, a book. We are not talking about a single electron or a single nucleus. All the atoms, all the electrons in the book, they are influenced by the neighboring electrons, neighboring nuclei. So let's see, if you try to vibrate around, move around, you will be hitting your book, you will be hitting the tables, you will be hitting your friends, you will be losing energy. So that damping term that we added is just a very simple model of you losing your energy. A very simple model, but nevertheless it grasps the basics that we would like to talk about. It grasps the basic phenomena. Maybe it will not have such a shape, but nevertheless it might have a different form, but that is the cause why the electric field loses energy. It is transferred to the electron, and the electron just gives it to somewhere else rather than back to the electric field. So the electric field as a whole loses energy. Now that is basically what we call dissipation. So, even in the case when you have this block sliding over inclined planes, basically what you do is, as the block is sliding down, it collides with the surface atoms, and those surface atoms, instead of take some energy, and instead of giving it back to our sliding block, it just gives it to somewhere else. So as a whole, the block loses energy. Similar phenomena appears here. The electric field gives some of its energy to the electrons. Although the medium is not conducting, still, due to the polarization effects, the charges are allowed to move around, but as they are moving around, they also collide with other objects, and as they are colliding with other objects, they will give some of the energy that they took from the electric field to those other objects. So at the end, the electric field loses its energy. And that since the energy of an electric field is related to, let's say, its amplitude, if the electric field loses energy, it just means its amplitude will get smaller. In a more realistic case, maybe it won't be exponential. It might have some other form, but the basic idea that the magnitude of the electric field will get smaller, it will still stay the same.
O zaman böyle sürttüğümüzde aslında elektrik alanından aldığımız enerjiyi ısıya mı dönüştürüyoruz?
Correct. You see, what you are doing is when an object is sliding on top of some other object, the collisions are basically electromagnetic forces. So my hand has its electric field. It collides with the atoms of it influences the atoms of my other hand, and they acquire kinetic energy. And that kinetic energy, due to these electric forces, that kinetic energy is what we call the heat. So basically the energy of one of my hand, it just becomes the heat of the other hand, or even of the same hand. Now, what about the velocities? What is the phase velocity? What is the group velocity of this medium? Well, to find the velocity, the speed, let's say the phase velocity, it is just omega over k. Now the group velocity is del omega by del k. So let's try to find some of these expressions. Basically, we need to express omega as a function of k to be able to evaluate these in this medium. So we know that k tilde over omega is equal to 1 over epsilon tilde mu. This is equal to 1 over square root of mu. I will just assume mu to be a constant independent of frequency. Well, epsilon tilde, we already have it. That is, let me put the epsilon 0 over here also. You see, we had already calculated epsilon. One plus nq squared divided by k minus, no, not that one, nq over m squared, omega 0 squared minus omega squared plus I omega gamma to the power 1/2. Well, minus 1/2. Well, you see, most of the time the deviation from 1 will be small. So in that assumption that this number is small, we can just make a Taylor expansion of this thing. So k tilde over omega is equal to c. Mu is almost mu 0. 1 over square root of mu 0 epsilon 0 is just c times 1 minus 1 over 2 nq squared over m squared divided by omega 0 squared minus omega squared plus I omega gamma. Now k is just c times the real part of k tilde. This is the real part of c omega 1 minus 1 nq squared over 2m divided by omega 0 squared minus omega squared plus I omega gamma. I should take the real part of this thing. This is c omega times 1 minus nq squared over 2m omega 0 squared minus omega squared divided by omega 0 squared minus omega squared squared plus omega squared gamma squared. Now this is my k. It's a function of omega.
Omega 2.
Apparently I made a mistake someplace.
Omega k cinsini almamız gerekmiyor mu?
Hmm?
Omega'nın k'nin fonksiyonu olması gerekmiyor mu?
Just invert this if you want. Well, this should be, I made a mistake somewhere. This should be 1 over c. So probably my mistake is, now k over omega is 1 over v. 1 over v is, probably you were mentioning this, right? 1 over v is square root of epsilon mu. So this is square root of epsilon mu 0 square root of epsilon 0 mu 0. This is plus 1/2. This is plus, here I have 1 over c. So this is plus, here I have over c. Yes. This is plus. And kappa is the imaginary part of k tilde. If you just take to take the imaginary part, just multiply with the conjugate of this one, the numerator and denominator. And you would see that this kappa is omega over c minus omega gamma n q squared over 2m divided by omega 0 squared minus omega squared plus omega squared gamma squared. Well, let's see. K over omega. Let's try to sketch Kc over omega. If you look at that top line, Kc over omega is just 1 plus that number. So let me plot Kc omega minus 1. 1 is a constant.
Is a function?
As a function of omega. So what does it look like? Well, let's see. When omega is equal to omega 0, it crosses 0. And when omega is larger than omega 0, it is less than 0. When omega is smaller than omega 0, it is larger than 0. When omega goes to plus or minus infinity, it's just 0. It just goes to 0. So it basically looks like this. This is how it looks like. And at exactly omega is yes. You see Kc over omega minus 1. Now K over omega is what we call the inverse group velocity. Phase velocity, V phase, minus 1. If the phase velocity is larger than the speed of light, this ratio is less than 0. This quantity is less than 0. So here we have all this region where Kc over omega minus 1, which is nothing but c over the phase velocity minus 1, it is less than 0. So in this frequency ranges, above the resonance frequency, the phase velocity is larger than the speed of light. Nevertheless, if you calculate the group velocity, you will find that it is still less than the speed of light.
Yani hocam elimizde böyle bir dalga grubu var işte. Dışta grup velocity. Bu ışık hızıyla gidiyor ama içindeki oscillation ışıktan hızlı mı?
Now that package goes with a velocity less than the speed of light. The peaks inside seems to move faster than the speed of light. Well, most of the time, this is one of the claims when they claim that they have observed faster than the speed of light phenomena. Well, it's over here. Sure, detector observes the energy, basically. Energy is carried by these packages.
But mean of the package is not.
The maximum of the package, let's say, it moves with the phase group velocity, which is less than the speed of light. Well, let me see. Let me not open it. let us end the lecture here. I'm running out of charge. If you have questions, come to me and we can look at the display.